So we're saying there were two real rational roots. They don't say the word real, but if they're rational, they can't be imaginary or complex. So I said we're going to go real quick through these. So the A is 1, the B is 8, the C is 16, and when we do the B squared minus 4AC, which is good practice for the big quadratic formula, the full formula, that's 64 because 8 squared minus 4 times A times C. That's 64 minus 64. Remember to do this part first. 64 minus 64 is 0, which means we're only going to have one solution. Because it doesn't matter, square root of 0, adding and subtracting when you start looking at the bigger picture. So if you add 0 or subtract 0, you get the same thing. So that's why there's only one answer. Typically, a quadratic has two answers. But as we've said before, when you have a perfect square, and that's what that is, that one answer is repeated or duplicated, and that's why we only have one. Remember, in the graph of a perfect square, the graph comes down, touches the x-axis, and goes back up. That's just how that works, and so that vertex right there is the solution. In this case, it would be at -4, because that is the solution of that particular quadratic. So let's look at a real problem here. So A is 1, B is 5, C is 6. Plug in. Negative B, the opposite of the 5, is -5, plus or minus. B squared is 25 minus 4 times A times C all over 2 times A. Now, order of operations and things like that matter here. So inside the parentheses where the radicand is, as we've been doing when we were just doing the discriminant, you're going to get a minus 24 because you do the multiplication first. And then the last thing we see inside the radical is a 1. And so that's -5 plus or minus 1, because the square root of 1 is 1 there. Okay. Now look, you've got two things here. You've got -5 plus 1 and -5 minus 1. What is -5 plus 1? -4. Divided by 2, -2. What is a -5 minus 1? -6. Be -3. And so my solution set is -2, -3. Now we could have done this by factoring. You're like, well, why didn't we? Because we wanted to practice this. But we could prove or confirm by factoring that those two really are the solutions. Different problem. One of the things that I notice immediately, and you need to learn to notice immediately, is we do not have equals 0. So we need to first subtract 33 from both sides so that we can easily identify the A is 1, the B is -8, and the C as a -33. So when we look at our quadratic formula, if you write the formula every time, it just helps you to remember the formula over time. So the opposite of B is a positive 8, because B is a -8, plus or minus B squared, which is 64, minus 4 times A times C, all over 2 times A. That's 2 times 1. A is often 1, but it doesn't have to be, so be careful. Don't get in the habit of just doing 2 times 1 every time. Be observant of what the A is. So you have 8 plus or minus. Now this is 64, and a -4, I'm up here. -4 times 1 times -33, I believe, is a positive 132 over 2. So that's 8 plus or minus 64 plus 132 is 196 over 2. Now, it just so happens that 196 is a perfect square, which is convenient. So you get 8 plus or minus, I got over 2. Square root of 196 is 14. And so when you do 8 plus 14, you get 22. Divided by 2, you get 11. When you do 8 minus 14, you get negative 6 divided by 2, which is negative 3. And that's your solution set. Notice that because this is a perfect square in here, you get two real solutions, two real rational solutions. Same. Got it. Go. So we need to do the same for this one. I would suggest you stop the video, do it, practice for yourself. You really should stop the video, practice for yourself. See if you can do this. You need to put your brain to work on ones where you can see the answer rather than wait to get to the classwork or assignment and then not know if it's right or not because we don't have it back to the book with the way we're doing these workbook assignments. So they tell us up front that this is one rational root, so you practice this as well. This is a big number for a C, but, it works. And so when you go through the process, you should have paused the video and done it for yourself, but the solution is 17 is one real solution, and the reason why is because this is a perfect square, because that's a square, it's x squared, that's a square, it's 17 squared, and that is twice their product. So that's why there's only one solution. Same kind of thing there. I don't want to worry you out with this. But let's look at this one, which is irrational roots. So I'll put these up here out of the way. A is 1, B is a negative 6, C is 2. So I'll write the formula. Just write the formula. Don't be lazy. Write the formula. Practice writing the formula. The opposite of B is a positive 6 because B is negative 6. B squared, negative 6 squared, is a positive 36. B squared is always positive. A is 1 and C is 2. All over 2 times 1. So working inside the radical with the radicand and doing the multiplication, I get a minus 8. And 36 minus 8 is 28. And I get that. I want to bring that over here because I got more work to do. And once upon a time, we learned about the square root of 28. Now, we didn't do it very well because we got our Alg 1 class interrupted. But the square root of 28 is also known as 4 times 7, square root of 4 times 7. Why do we do it that way? Because 4 is the square hiding in there. The square root of 4 is 2 times 7. So I'm going to bring that back over here. 6 plus or minus 2 times the square root of 7. Because that's what the square root of 28 is in simplified form. Now, it just so happens, and you probably wouldn't see this, but the numerator has a common factor of 2. So I'm going to take out the 2 from both of the terms. You should be able to redistribute and get back what you started with. I don't know how that 28 became 28 because it's not. It was a 2. It's still a 2. And then these 2's cancel. And the final answer is 3 plus or minus the square root of 7. So those are two irrational solutions. 3 plus the square root of 7 and 3 minus the square root of 7. You see they got it to here. And then they finished it. 3 plus the square root of 7, 3 minus the square root of 7. These are the decimal approximations. If we graphed it, one solution is between 0 and 1. The other solution is between 5 and 6. But we wouldn't be able to have these cute solutions if we hadn't used the quadratic formula. So we need to know how to do that. But you can confirm stuff with the graphing calculator as far as location. The graphing calculator will not give you those. It will give you those, or at least estimated or approximate those. So that's how this works. I mean, this is what we're doing. And then we just keep doing the work. You should pause the video. You should take a peek at this and see if you can do this for yourself. Okay, this obviously says complex roots, so let's get started. First of all, I see that we do not have equal to 0, so I'm going to fix that by subtracting 6x on both sides. Notice I put the linear term, the 6x, in the middle because that's where it typically belongs. That's where we think of it belonging. So a is 1, b is -6, c is 13. I mean, I'm just saying, if you find things are not in order, put them in order. You should do that in your closet, in your wherever. Put things in order. Okay. So x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Opposite of b is a +6 because b is -6. b squared is 36 minus 4 times a, which is 1, c, which is 13, all over 2 times a. So that's 6 plus or minus over 2. And here we get 36 minus 4 times 13 is 52. So that's 6 plus or minus the square root of -16. And that's why we've got this complex root thing up here, because we got the square root of 16. You should remember, hopefully you do, as I bring this over here, that's 6 plus or minus 4i. The I because of the negative, the 4 because of the square root of 16. Got a common factor of 2 again. So take 2 out of both terms of the numerator. It cancels with the denominator 2. Well, it would help if I had taken it out of both. That's 3. And so the answer is 3 plus or minus 2i. It's actually 3 plus 2i and 3 minus 2i.